I'm very excited about this Gardi supercomputer grant. We've got a bunch of new experiments planned, and there's no way we could do this work without NCI support. We will greatly enhance our contribution to the World Climate Research Program Coupled Model Intercomparison Project. That's the most comprehensive suite of climate model experiments ever conceived. We have detection and attribution experiments that go right to the heart of the climate change debate by separating natural forcings from human emissions, like carbon, which warms, and sulfate aerosols, which cool. Our first Earth system contribution to this international project includes the direct role of carbon in climate system feedbacks. The models show the effect of policy decisions on determining potential future climates. We also have exciting new upper atmospheric chemistry capability. These models are our primary tool for investigating future climates. The new grant also allows many more ensembles of experiments. Larger ensembles reduce the uncertainty in our future projections. The work informs next year's Intergovernmental Panel on Climate Change assessment report. It is a huge, coordinated international effort. The deadlines are tight, so I can't underestimate the value that the Australian Leadership Computing Grant is adding.
As events of the last 2 summers have shown, Australia is a climate-exposed nation where communities and industry require favourable climate conditions to be sustainable. I'm Richard Mateer, and I lead the CSIRO Decadal Climate Forecasting Project. The project is working to provide useful climate information on the annual decadal climate scale to enable Australian communities and industry to become more resilient to climate variability and extremes. NCI's generous compute allocation enables us for the first time to generate a large ensemble of decadal climate forecast, a unique dataset to investigate the utility of the forecast for the benefit of Australian communities and industries. The forecast dataset was not feasible without the additional support from NCI and will place Australia at the forefront of international efforts in decadal climate forecasting. The dataset will contribute to the World Meteorological Organization's grand challenge in near-term climate prediction and will be the only contribution from the Southern Hemisphere. Such an exciting dataset are used for many years and will train new research into the application of climate forecasting for the benefit of Australia. This is an exciting time.
Our best theories for how galaxies grow over cosmic time tell us that enormous black holes, millions of billions of times the mass of our Sun, play a fundamental role in this process. They can launch powerful jets that interact with their surroundings and can grow to millions of light years in length. Indeed, we see striking examples of this in the real universe. The goal of this NCI project is to understand how this process works in detail.
Over the next several years, telescopes such as the Square Kilometre Array will observe tens of millions of galaxies and black hole jets. Our NCI project will provide a theoretical framework for understanding those telescope measurements. We are combining our best knowledge of the physics of galaxies and of black hole jets to form a single picture of how these cosmic ecosystems evolve.
I'm Evatt Hawkes from UNSW Sydney. In our project, we're looking at a new gas turbine combustion concept that's used in electricity generation. The concept we're studying is called axially staged combustion, which splits the process into 2 distinct phases that are governed by different combustion modes. These systems have been developed to improve efficiencies, but also to improve operational flexibility, enabling greater synergy with renewable energy sources and the burning of alternative fuels such as hydrogen. So the thing is, while several manufacturers have deployed these systems, nobody really understands what's going on in the second combustion stage. It's basically impossible to get in there and make detailed measurements, so our project instead employs detailed simulations. Computationally, these simulations are really expensive since the flows inside the combustor are very turbulent, and since turbulent flows have a large range of length scales and time scales. For example, if the combustor diameter is something like that, then the very smallest scales of flow motion that we would need to resolve would be in the order of micrometers in size. Tackling such problems is only possible with a machine like Gardi and only with a grant of this scale. The outcomes will be improved understanding of combustion in these axially staged gas turbine systems, information that we anticipate will be very useful to industry in further reducing emissions and enabling higher levels of hydrogen fueling.